In the last video, we reviewed some fundamental concepts about Taylor polynomials, and we talked about the idea of using a Taylor polynomial to approximate a function f of x. This will allow us to find values of the function near the point at which we center using a polynomial. It's much nicer to use polynomials rather than transcendental functions or rational functions or any other kind of function. Polynomials are much easier to work with. Whenever we have an approximation, there's always going to be some error involved. We call the error the remainder for Taylor polynomials. There is a way, using this Taylor's inequality, to determine how bad the error is, and this will let us know how close our approximation is to the true value of the function. We practiced using Taylor's inequality in the example from the last video, but this can be a fairly tricky concept to understand how this Taylor's inequality works, so we'll practice it with a few more examples. Let's take a look at example 2. We have the function natural log of x. We are centered at 1, and we are going to use a degree 3 Taylor polynomial. We're looking on the interval from 1 to 1.5, so we're thinking of x values on that interval. We're going to start by finding the degree 3 Taylor polynomial, and then we'll use this inequality to talk about how good the approximation is over this interval. So we've got our function f of x, which is the natural log of x. Let's write down where we're centering. We're centering at a equals 1. And we want to use a degree 3 Taylor polynomial, and we're focusing on the interval from 1 to 1.5. So we're really only interested in approximating this function over this particular interval. Let's first do part A, which is finding the third degree Taylor polynomial for the function. And let's just write out in general what the third degree Taylor polynomial is. It's f of a, and we'll go ahead and use 1, f of 1 plus f prime of 1 divided by 1 factorial times x minus 1 plus f double prime of 1 divided by 2 factorial times x minus 1 squared. And then the third term, f triple prime evaluated at 1, x minus 1 cubed divided by 3 factorial. In order to find this polynomial, we really only have to find the value of the function at 1, and then the first, second, and third derivatives. So we're going to make a table of derivatives just like we did when we were solving Taylor series problems. Setting up the table, we have n. We'll look at the nth derivative evaluated at x, then the nth derivative evaluated at 1. And we need to go up to n equals 3 here. So 0, 1, 2, 3. The 0th derivative, that's just the original function, natural log of x. We plug in 1, natural log of 1 is 0. So f of 1, that's natural log of 1, that's just 0. Now we find the first derivative. First derivative is the derivative of natural log of x, which is 1 over x. We're plugging in x equals 1, so f prime of 1 is 1 over 1, 1. So our second term here is 1 times x minus 1. For the second derivative, we want to think of 1 over x as x to the negative 1. So the derivative, using the power rule, negative x to the negative 2, which is the same as negative 1 over x squared. Plug in 1, and we have a second derivative of negative 1 divided by 1, which is negative 1. So we have negative 1 divided by 2 factorial times x minus 1 squared. Third derivative, we bring down the negative 2. Negative 2 times negative 1 is just positive 2. So 2x to the negative 3. Plug in 1, f triple prime evaluated at 1. This is 2 over 1 cubed. So this is just 2. The final term is 2 divided by 3 factorial times x minus 1 cubed. This polynomial looks very close to the function natural log of x for x values around 1. And if we plug in different x values close to 1, we will find very close approximations to the function natural log of x. So if we restrict ourselves on this interval from 1 to 1.5, we have a very good approximation for the natural log function. Let's take a look at this visually in Desmos. Here is the degree 3 Taylor polynomial that we just found. It doesn't look all that thrilling. There it is. We're restricting ourselves to just thinking of the interval from 0.5 to 1.5. That's really where we're interested in looking at what happens. So let's compare what this function looks like, this polynomial, to natural log of x from 0.5 to 1.5. Look how close they are. Natural log of x matches up really well. They only seem to differ a little bit here near the tails. So if we want to approximate natural log of x using a polynomial, we'll get very close approximations just with a degree 3 polynomial. Now that we've seen in Desmos how close this polynomial approximates the function natural log of x, let's answer part B of this problem. For part B, we want to find numerically how close the approximation is. We want to use Taylor's inequality to estimate the accuracy of our approximation. So let's write down Taylor's inequality. The absolute value of the error, which is the remainder, is less than or equal to m times the absolute value of x minus a. A again is 1, so x minus 1 to the n plus 1 divided by n plus 1 factorial. This is the expression that we get from Taylor's inequality, and we want to look at this expression on the interval from 1 to 1.5. So all the x values from 1 to 1.5. Probably the trickiest part of this Taylor inequality is finding the value of m. M is defined as being an upper bound of the n plus first derivative. So we want to find a value for m such that the n plus first derivative of the function, absolute values, is always less than or equal to m on our given interval from 1 to 1.5. So first we'll start by finding the n plus first derivative. N equals 3, so we need one more derivative here. We need the fourth derivative. The fourth derivative is negative 6 x to the negative 4. I'm going to write it as negative 6 over x to the 4. I want the absolute value of this, so we'll just put absolute values here. And taking the absolute value of negative 6 over x to the 4, we just have positive 6 over x to the 4. All of the x values are positive. So the absolute value of the fourth derivative is this right here. That's the absolute value of the n plus first derivative. We want to find a number m such that this function is always less than or equal to m on the given interval. Or we could think of this as maximizing this function on the interval, and m will be the maximum value. So what is the very largest that this function gets on the interval from 1 to 1.5? We want to know what is the maximum of this function on the interval from 1 to 1.5. That will be the value of m. In general, when we find the maximum or minimum of a function, we have to find critical numbers and then figure out if we have maximums or minimums at the critical numbers using like a first derivative test or the closed interval method, something like that from Calculus 1. That's more work than what we want to do here, and we don't have to do all that work. For this particular example, we're going to think of what happens if x gets bigger. What happens to this function? Well, as x gets larger, the denominator grows, and if the denominator grows, then the whole thing gets smaller. If we divide by bigger and bigger numbers, the entire fraction gets smaller and smaller. So this will have a largest value when x is smallest. Well, when x is smallest is when x equals 1. So the maximum occurs when x equals 1. So this will always be less than or equal to 6 divided by 1 to the fourth, which is just 6. 6 is an upper bound on this function from 1 to 1.5. The function is decreasing on the interval from 1 to 1.5, so its largest value will occur at the smallest value for x. So we have m equals 6. We can plug that now into Taylor's inequality. So for Taylor's inequality, we have 6 times the absolute value of x minus 1. N is 3, so we're raising to the fourth power here, dividing by 4 factorial. That's an upper bound on the error. This works for all the x values on the interval from 1 to 1.5. So if we want to know for any x value in this interval how far off our approximation is, we would just plug that x value in here for x, and then this upper bound would tell us, worst case scenario, how bad the error is. So over the entire interval, what's the very largest that the error ever gets to? Well, the very largest that the error ever gets to is when we have the largest value in here that we're raising to the fourth power. This happens when x is furthest away from the center. This is an important concept. Our approximation will be the worst when we're the furthest away from the center. So if we want to know worst case scenario over the entire interval, we're going to plug in the furthest distance from the center in for x. Let's do that. So we plug in, well, we keep the 6 divided by 4 factorial times the absolute value of 1.5 minus 1. Well, that's just 1/2. 1.5 minus 1, 0.5, 1/2. So this equals 6 over 4 factorial times 1/2 raised to the fourth. This number equals 1 divided by 64, which is approximately equal to 0.016. Well, now that we've got this number, what does that tell us? This number tells us that at worst, the very most error that we could possibly have is 0.016. In general, the approximations will actually have much less of an error. But when we use this Taylor polynomial of degree 3 to approximate the function natural log of x, all over the interval from 1 to 1.5, the error will always be less than 0.016. That's the very worst case scenario. It's an upper bound on the error. Now that we've found an upper bound for the error of our polynomial approximation, let's take a look at example 3. In example 3, we want to use the degree 3 polynomial we just found to estimate natural log of 1.5. And we know how far off this will be. Worst case scenario, the most error that we have is 0.016. So when we approximate natural log of 1.5, we're going to be within 0.016 of the exact value. Let's estimate that natural log of 1.5 using our Taylor polynomial. So we'll write down the Taylor polynomial here for example 3. Our Taylor polynomial that we just found, t sub 3 of x, I'll write it a bit simplified. It's x minus 1 minus 1 over 2 factorial, which is just 1/2, times x minus 1 squared, plus 2 over 3 factorial, that simplifies to 1/3, times x minus 1 cubed. There's our degree 3 Taylor polynomial. We're going to use this to approximate natural log of 1.5. So this polynomial is approximately equal to natural log of x for x values close to 1. So natural log of 1.5 is approximately equal to this third degree Taylor polynomial at 1.5. We're going to plug in 1.5 for x. So we have 1.5 minus 1 minus 1/2. And notice in the parentheses here, 1.5 minus 1, that's always 1/2. So instead of writing 1.5 minus 1, I'm just going to write 1/2. So 1/2 squared plus 1/3 times 1/2 cubed. If we wanted to, we could just sit down and chug through the math to simplify this expression. Notice that all we're doing is adding, subtracting, multiplying, dividing. That's what always happens in a polynomial. That's all we do. We add, subtract, multiply, and divide, and we can do that by hand if we really need to. Calculators and computers can do that really quickly, very efficiently. So just by adding, subtracting, multiplying, and dividing in a polynomial, we can approximate crazy function values like natural log of 1.5. How would we calculate this expression if we didn't have an approximation like this? Apart from plugging it in a calculator. We'd really have no clue. What's natural log of 1.5? I don't know. Well, here's a very close approximation. Rather than simplify this all out by hand, I'm going to plug it into Mathematica and see what I get. This approximately equals 0.417. So natural log of 1.5 is pretty close to 0.417. How close is it? It's within 0.16. Worst case scenario, that's how far off my approximation is. So I can say with 100% confidence that natural log of 1.5 is equal to 0.417 plus or minus 0.016. Not only do I have an approximate value for natural log of 1.5, I know how close my approximation is from Taylor's inequality. And we have an upper bound on the limit. Worst case scenario, how bad the error is. Upper bound on the limit? What's an upper bound on the limit? Good grief, get your terminology right, dude. I lost my train of thought. I don't know where I am anymore.